Hello, so this video is about the Arrhenius equation. It's basically an equation which describes the rate of reaction. And I've given you the equation in the top right of the screen here. But for the beginning of this video, I'm not going to talk about it too much. But what I will say is that the equation itself is really underpinned by some concepts that you have probably already covered. And so what I'm going to do in this video is give a brief recap of the real core topics which underpin the equation, and then start talking about how they contribute terms to the equation. And so hopefully by the end of the video, you should have a nice, deep understanding of what the equation means and where all its different parts come from. And hopefully it should be a bit more than just letters on a page. And so the topics I think that we really need to briefly recap to understand this is firstly collision theory, then energy profile or enthalpy profile diagrams, and then finally Maxwell-Boltzmann distributions. And so I will recap these, but I'll do that very quickly. And if you find that you either haven't covered those before or that it's going a bit fast, I'd recommend you look at videos on those specific topics. They're just more there to help you understand the equation itself. And hopefully that'll make sense once I get to it. So in terms of these topics, so collision theory is this idea that in order to react, molecules must collide. But not only must they collide with the right orientation. So that is to say, if, for example, you're reacting A, B, and C to give you A and B, C, you need your B and your C to collide with each other, because that's where you're forming a bond. If the C comes along and hits the A, that's not going to do any good, because the C is not reacting with the A. So you need your species to have the right orientation. And so within a given mixture, you're going to have a certain chance that the molecules bump into each other in the correct orientation. That's going to be quite statistical. They're just going to be bouncing around, and there's a certain percent chance they're going to bounce there. One of the ways you can increase the chance of a reaction then is by making there be more collisions, because the more collisions, the more successful collisions. If you've only got a 2% chance of a successful collision, if you change from having 100 collisions to 200, you're still going to double the number that are successful. So we can speed up a reaction then by increasing the pressure or the concentration or the surface area, for example. Okay, and this is actually explained in the A term here, which I'll come to later on. But not only do particles have to collide with the correct orientation, they have to collide with the correct energy, because we're breaking and forming bonds, so we need some energy involved. And this is explained nicely by energy profile diagrams. So if we have energy along the y-axis, time or reaction progress along the x-axis, what we know is that initially our different species are at their own energy level. Then as they come closer together, as we start breaking and forming bonds, the energy of the system increases till we reach a maximum. And then as the reaction continues, the energy decreases until we have formed our products. And in this case, I've drawn the reactants at a higher energy than the products. So this is an exothermic reaction. But you can, of course, also have endothermic reactions. But for our purposes here, what we really care about is this distance here between the reactant base energy and the maximum in the energy profile diagram, the top of this hump. And that's what we call the activation energy. That's the energy we need to overcome this hump in order for the reactants to become the products. And so if we want to speed up a reaction, we can lower the activation energy by using a catalyst. So that's something which speeds up a reaction by providing an alternative reaction pathway. That will in some way influence the hump here, almost certainly lowering it. But also, if we don't want to directly influence the activation energy, we can simply give our species more energy. So more of them can overcome this hump. And quite often the way we will do that is by using an increased temperature. And so one of the ways to think about this is using Maxwell-Boltzmann distribution. So this is the idea that at a given temperature, all of your species don't have the same energy. They have a distribution of energies. So if this is your number of species here, number of particles, say, and this is your energy, you have this spread. So you have relatively few at very low energies, relatively few at very high energies, and quite a lot in the middle. And if you increase the temperature, you essentially shift the average energy and also increase the number at high energies. So that is to say, if your activation energy was here, in the red curve at a higher temperature, you're going to have more particles with enough energy to overcome the activation energy. So from this, we know then that also increasing the temperature can help speed up a reaction. And really, our Arrhenius equation helps explain that and really quantify it. Okay. So the Arrhenius equation then, we can now start to discuss the individual terms. So we have K, this is the rate constant, so this is a measure of the rate of reaction. The bigger K, the faster our reaction, equals A. This is what's called usually the A factor or the prefactor term. And this is actually a measure of the chance of molecules colliding in the right orientation. The more likely that is, the higher A is. And also the number of collisions. The more collisions, the higher A is. So this can be influenced by increasing pressure, increasing surface area, increasing concentration, for example. Then we have an exponential term, e to the minus EA over RT. So I'll discuss the exponential in a minute. But for now, here's our activation energy. And here is our temperature that we discussed before. But note that they are within the exponential term. And so this explains why, if you double the temperature, you don't necessarily double the reaction rate, because it's not proportional. So there is a proportional change here between, as you increase A, if you double A, you're going to double K, but the same is not true here for T. And so, as I mentioned before, exponentials are a big topic in their own right. But what I'll tell you that's really important for this is that if you have e to the minus x, the bigger x is means the smaller e to the minus x is, and so k is smaller. So if the bigger x, the smaller the rate of reaction. So if the activation energy is big, the rate of reaction is smaller. That makes sense. Fewer particles can overcome the energy barrier. And if T is small, X becomes big and the rate of reaction is slower. So the higher T is, the faster the rate of reaction. Which again, that makes sense from our Maxwell-Boltzmann distribution, because the higher the temperature, the more particles there are that can overcome the activation energy. So really, this equation simply provides a quantitative underpinning to all of those sort of more wordy explanations that you've come across before, whether that's the collision theory, energy profile diagrams, Maxwell-Boltzmann distributions. So hopefully now you understand where all these terms come from and how exactly we can influence the rate of reaction to increase it or indeed to slow it down. Thank you.